Okay, in this problem we have this car right here that's accelerating, and we are told that it has a center of mass at this point G. And G is 1.25 meters from the front wheel. This is the front wheel. And 0.75 meters from the back wheel. And it's also 0.3 meters off the ground. So we're asked to determine what this acceleration is if the back wheel slip. The back wheel slip means is a frictional force, and we're given that the coefficient of kinetic friction is equal to 0.25. So what I've done is I've copied this picture twice so I can draw my free body diagram. And on my free body diagram, I want to identify all the forces that are acting on my system. We know the back wheel slip, so I have a frictional force. But what direction does this frictional force act? Well, if my car is moving this way, and my car is moving this way, and the wheels are turning like this, the frictional force is going to oppose the movement of the wheel. So my wheels are moving counterclockwise. My frictional force is going to act in this direction. So my frictional force acts to the left. I also have a normal force on both my wheels, so we'll just call my front wheel the normal force A, and my back wheel my normal force of B. And the last force that we know we have is we have the weight of the car, and we are given where its center of mass is, and we know our weight acts right through the center of mass. So this weight is going to be 2,000 times 9.81. So these are all the forces that are acting on my car. What about the accelerations? So on this car, on this problem, I'm going to define, I have a XY directional, X is positive to the right, Y is positive up. So I'm going to assume that my acceleration is in this positive direction. So my acceleration of G is just this acceleration of G in the positive direction times the mass, which is 2,000. And if I'm wrong, then this will come out to a minus sign, and it'll tell me my acceleration is actually to the left. So we know we have three equations we can use. We have the sum of the forces in my x is equal to a mass times the acceleration of g to the x, g in the x direction. The sum of my forces in my y is equal to a mass times the acceleration of my center of mass in the y direction. And I have the sum of the moments about point G is equal to this moment of inertia times my angular acceleration. Now, this problem is a purely translational problem. That means none of my car does not rotate as it travels. My car is not turning over. It's not in a car crash, which is probably good. So this sum of the moments about point G is going to simplify and just be equal to 0. And this is a property of translational problems, that there is no rotation, and this term right here suggests that there would be some rotation. So with translational problems, it's just the sum of the moments about the center of mass is equal to 0. Now, the sum of the forces, this is also going to be equal to 0, but for sort of, it's not a property of a translational problem. It's a property of the car is only accelerating towards the left. It's only accelerating this way. There's no acceleration in the up and down direction. So some of my forces in the y are just going to equal to 0. If I fill in the rest of these equations, I'm going to have a frictional force, and just for completeness, let's call our frictional force this 0.25 times NB. Sometimes I forget to substitute this 0.25 NB in, so 0.25 times the normal force at B, and then you look at your problem and you're like, I got 4 unknowns and 3 equations, and that's not good. So let's just substitute that in right now. If I I sum my forces, I'm going to have this minus 0.25 times this normal force of B. That's my only force in this x direction, and this is going to be equal to a positive 2,000 times my acceleration of my center of mass. Now, if I look at the sum of the forces in the y, I'm going to have, let's call that positive and this way positive. So I'm going to have a minus 2,000 times 9.81. That's the weight right here, plus a normal force at B, plus my normal force at A, is equal to 0. So my normal force is right here and right here. And now let's take the sum of the moments about point G. Point G is the center point, and it's going to have the only force that has no moment about it is the weight, because the force of weight goes right through the center of mass. So if I call this my positive direction of rotation, I'm going to have my frictional force is going to want to go tail first, so it's going to be a minus. So if this frictional force is rotated around point G, it wants to rotate tail first, and I have minus 0.25 times NB times the perpendicular distance, which is 0.3. My normal force of B wants to rotate head first, so it's a plus NB times this perpendicular distance, which is 0.75. And NA wants to rotate tail first, so it's minus NA times 1.25, and this is equal to 0. So when I combine this, I'm going to get a 0.75 NB, and then I'm going to have a minus 0.075 NB. And this is going to be equal to 1.25 NA. I just moved this to the other side of the equation. So this is going to be 0.675 times the normal force of B is equal to 1.25 NA. And we're going to get 0.54 NB is equal to the normal force at A. So now we have an equation for NB and NA. What we can do, we can bring it back into this equation right here. So we're going to have 0.54 NB plus NB and minus 19,620. So we can solve for what our normal force at B is, and our normal force of B is going to be equal to 12,740 newtons. We can take this normal force, we can put it back into this normal force of A, and we can get NA is going to be equal to 6,879 newtons. And we can also take this normal force at B, plug it into our sum of the forces equation, and get what this acceleration of G is. And when we do that, this NB just goes right here, and we're going to get the acceleration of G is equal to minus 1.59 meters per second squared. And look at that, we have a minus sign. So our car is actually accelerating in the opposite direction that we think it is. It's actually accelerating 1.5 meters per second squared towards the left, this way. So this is what our acceleration of g is.